All right, let's just dive right into this. Welcome to this explainer, where we're going to unpack a massive environmental footprint that's, well, kind of hiding right in plain sight. Specifically, we're looking inside the daily cleaning routines of a cooked sausage food processing plant. We're going to explore exactly how resource draining these operations actually are, and more importantly, we'll walk through a completely brilliant green engineering makeover that transforms the entire process. So, ask yourself, how do you actually clean an entire sausage factory? Honestly, you might think it's just about some heavy-duty soap and high-pressure water, right? But blasting away stubborn fats, baked-on proteins, and that thick grease out of complex industrial equipment, it's actually a highly resource-intensive and chemically aggressive daily battle. I mean, we aren't just washing dishes here. This is a heavy-duty industrial necessity just to ensure food safety and prevent dangerous microbial growth. And the conventional way they do this is something called cleaning in place, or CIP. But the dirty secret of traditional CIP is that it leans way too hard on a brute force methodology. We're talking fixed timers, extreme heat, and really harsh chemicals that just waste immense amounts of water and energy while simultaneously creating highly polluted effluent. Instead of cleaning until the system is actually clean, the old method just runs boiling water and chemicals on a clock, completely regardless of whether the equipment actually needs it or not. Looking at this baseline process flow diagram, you can see this massive, continuous loop. Water and harsh cleaning fluids get pumped from those storage tanks at the bottom, pushed all the way up through the meat grinders, blenders, emulsifiers, and smokehouses, and then, tragically, they're mostly just discarded. All that thermal energy, all that water, literally just flushed out after doing its job, which puts an absolute massive strain on downstream wastewater treatment facilities. And honestly, the sheer toxicity of what's flowing through those legacy pipes is staggering. If you look at this breakdown, the conventional chemicals cause severe collateral damage. You've got extreme pH swings from sodium hydroxide, toxic air vapors from chlorinated degreasers, and dangerous nutrient loading in local water systems caused by phosphoric acid. Sure, these chemicals are highly effective at stripping grease, but they create an absolute nightmare for both the environment and the poor workers who have to handle them every single day. So let's get into Section 1, the Green Chemistry Makeover, Smart and Safe Substitution. First up on our Redesign hit list is the primary alkaline cleaner. By swapping out severe, literally flesh-burning sodium hydroxide for a much milder sodium carbonate, which you might know as soda ash, the plant achieves a massive safety victory. The soda ash still totally does the job of breaking down heavy animal fats and proteins through saponification, but it vastly reduces the risk of accidental chemical burns for the operators. Plus, it stabilizes the wastewater pH before it even leaves the building. It's a total win-win. Next, we've got to tackle those heavy-duty degreasers. Instead of relying on chlorinated alkaline detergents that just fill the enclosed factory with dangerous airborne volatile organic compounds, or VOCs, this redesign brings in a bio-derived coconut-based surfactant blend. It is incredibly effective at lifting caramelized soils, but the best part? It breathes cleanly. That means literally zero toxic air emissions for the workers out on the factory floor. The redesign also takes aim at downstream environmental disasters. To clear out hard mineral scale from all that stainless steel equipment, the conventional method relied on phosphoric acid. But discharging that phosphate drives these incredibly destructive algal blooms in local rivers and lakes, literally suffocating aquatic ecosystems. By switching to a highly biodegradable lactic acid, the plant gets the exact same descaling power, but completely eliminates that tragic nutrient loading. Moving on to Section 2, Smart Systems and Recycling. This new smart sensor-driven life cycle, it's an absolute game changer. Why? Because it completely stops relying on guesswork. Inline sensors are now continuously monitoring the water's turbidity, conductivity, and pH. The instant those sensors detect that the pipes are actually clean and free of chemical residue, the automated system just terminates the cycle right then and there. It doesn't run for an extra 20 minutes just because a timer said so. This simple automation saves thousands of liters of treated water and chemicals every single day. When you put the old and new tank setups side by side, it really highlights a crucial shift. The old way required open air dilution and manually opening valves. The new way? It uses automated valve routing and fully enclosed dosing. By keeping concentrated chemicals locked inside a closed loop, we engineer out the human error of manual mixing and drastically reduce the chance of accidental, dangerous spills. And instead of just dumping all those intermediate rinse waters straight down the drain, this brilliant closed-loop integration actually captures them. It safely routes that lightly used water back to a holding tank so it can be reused for the very next pre-rinse cycle. It's such an elegant solution that drastically cuts down on freshwater consumption and stops open-air wastewater from pooling on the factory floor. This redesign also tackles a massive energy problem. Previously, the smokehouse generated intense heat to cook the sausages, which was then just vented away as waste. Meanwhile, the cleaning system was burning completely separate fuel to heat up cold water. This newly installed shill and tube heat exchanger actually captures that thermal energy exiting the smokehouse and uses it to preheat the incoming wash water. It completely eliminates a double loss of energy, making the whole factory vastly more efficient. Finally, let's look at Section 3. Designing a safer factory. Inherently safer design is this engineering philosophy where hazards are just eliminated right at the source. These 4 pillars prove that sustainability and worker safety really do go hand in hand. By substituting toxic chemicals for bio-derived ones, minimizing chemical volumes with smart sensors, moderating fluid transfers in enclosed pipes, and simplifying operations with automation, we simultaneously create a dramatically safer day-to-day reality for the plant workers. Good environmental design literally is good safety design. Even the factory floor itself got redesigned with passive safety in mind. Using gravity instead of electricity, the newly sloped floors constantly pull hazardous spills and wash water away from pedestrian walkways. Combined with dedicated drainage channels and chemical-resistant anti-slip surfaces, the physical architecture of the room is working to prevent slips and falls without needing any moving parts or human intervention at all. Putting it all together results in a complete paradigm shift. By integrating those biodegradable chemicals, the smart sensor feedback loops, and waste heat recovery, this facility has completely transformed a wasteful, hazardous necessity into an intelligently monitored, ecologically responsible system. The entire life cycle is closed-loop, safe, and wildly efficient. So, as we wrap up this explainer, it's worth taking a step back. We've seen how simple inline sensor loops and coconut-based soaps can completely revolutionize the environmental impact of a single sausage factory. It really leaves us wondering, doesn't it? What other invisible, resource-draining industrial systems are operating out there right now, just waiting for a smart, green makeover? Thank you for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.